Very good.
Okay, so perfect. It's my pleasure to introduce Jens Palsberg. We're previewing the session on quantum computing.
Very good. So quantum computing is the theme of this session, and exciting results in the papers, and can we understand what's going on. And so my job here is to persuade you that you will get a lot out of these talks. And I'll talk about 3 big problems in quantum computing, and I will show some concepts and notations of quantum computing, and then I'll give a highlight of each paper. And so let me begin with the big problems. So problem number 1. What is the role of quantum computing in our computing ecosystem? And so the thing to know here is that quantum computing is really restricted to linear algebra. And so it means that if quantum computing is a good fit for your application, it can go exponentially faster than classical computing. If it is not a good fit, then don't use it. And so it means that the future of quantum computing, of a quantum computer, is to be an accelerator just like a GPU. And so it means the driver is still going to be a CPU that farms out jobs to a GPU and a quantum computer. And now comes the usual question: how do we blend different models of programming into a single programming model so we can program at a high level? So that's problem number 1. Problem number 2 is then, what are the abstractions of quantum computing? And right now it's fair to say they don't have very many. There's one abstraction, which is everything is connected to everything else, which is not really true in many quantum computers, but that's an abstraction that people use. And we need more abstractions. And we also need types. Right now it's like everything is a qubit, and we need types to get our programs right. And another thing is that quantum computing is really at the bottom level a very imperative style of programming. And we should ask ourselves, what would functional programming look like, or other kinds of programming that we like at a high level? Third problem: how do we verify quantum programs? And this is a big deal, because if we are computing, so IBM has a quantum computer now with more than 400 qubits. If we are computing with that computer, our state vector is a vector of 2 to the more than 400 complex numbers. That's more complex numbers than there are atoms in the known universe. And how do we deal with this? So we cannot debug this in the usual sense. The state vector is just like way too big. So it would be much better if we knew ahead of time that our programs work. And so it means that whatever need we have for verification of classical programs, we have much more need for verification of quantum programs. So that was the 3 big problems. Now I want to say something about what if we don't know quantum computing already? What are then some of the key concepts? That is a qubit. Alpha and beta are complex numbers, and it's a vector of size 2, and there it is. That's a qubit. It's a unit vector. In quantum computing, when I say there's a state vector, it's a unit vector. And it's a unit vector of complex numbers. And the whole point is, if there are 400 qubits, then this vector then has a size of 2 to the 400. That's kind of where we are going with this. Then, once we have qubits, we could have 2 qubits. And here we have this Dirac notation that the quantum computing people love to use. This is really talking about 2 qubits, and here we have a superposition. And that's really just another name for a linear combination. I love linear algebra. I love the word linear combination, but that's not good enough for quantum computing, so they call it a superposition. And here we have a very particular superposition, a very famous one. So of course, here we have a vector of size 4 in special notation, another vector of size 4, and if you add all this up, you get this vector, and it's entangled. And so that's what the quantum computing people love to do. They create entanglement of qubits, and then they can get a lot of computing done. And the way they get computing done is with stuff like this, which very much look like some kind of hardware diagram, and that's because it kind of is. But it's also like a music sheet. Time goes from left to right. Every time you get to a box, a step of computing happens, and people like to call this a circuit diagram. This can also be textually represented, and then it just looks like machine code, and it kind of is machine code. And so here you see again this sort of these Dirac notation for vectors, and then every time you see a box, it's a matrix, and then if it's a little box, it's a 2x2 matrix, and if it's a big box, it's a 4x4 matrix. And that's kind of how quantum computing is done. You just apply a whole bunch of matrices, and then you can see over here there's some kind of meter. And what it does is that it extracts bits from qubits. And the way it works is, if you're working with this IBM quantum computer, 400 qubits, at the end you can extract 400 bits, which is kind of a little disappointing. We just had this enormous state vector, and all you get is 1 bit for each qubit. But that's how it works. So that's one of the constraints we have to live with in this world. Okay, so now I will touch on the papers of the session. So first we have the Qunity paper. And so what it does is that it addresses multiple of these big problems by blending classical and quantum computing into a single syntax, so a single unified syntax. And so it means that we can now write programs and then let the compiler worry about what goes to the classical computer and what goes to the quantum computer. And so here we have a famous example from the paper. It's a Deutsches algorithm written in their language. And we can see things like pattern matching. And then in the language, there's also exception handling. And there's other goodies like aliasing, but now interpreted both in a classical way and in a quantum way. And so they say we are generalizing classical computing to quantum computing. Second paper is instead interleaving classical computing and quantum computing. And so here we have a quantum teleportation written in their language. This is a variant of Quipper, which is Peter Sellinger's language from a long time ago, now extended with something called dynamic lifting, which is addressing a fundamental problem. So normally I think this is the way the physics people think. You generate a circuit and then you execute a circuit on the quantum computer. But what if you want to go back and forth, which is very important in quantum computing for many reasons. If you want to do that well, you need to be able to transfer information from the execution back to the generation of circuits. And how are you going to do that? Well, you're going to do that using dynamic lifting. I think lifting is sort of a concept that's known from two-level languages, and here it comes in. So here again, we have a language which has, so actually this is similar from the first paper to this paper. There's a type system, there's semantics. In this case, it has both a operational semantics and categorical semantics. And then these languages, the previous one and this one, then compile down to circuits, essentially. Third paper. So here we are into foundational verification in Coq. And so what they're doing here is that they want to verify programs like this one. This is a solution in their language called Q-while to a famous problem at least in quantum, called the hidden subgroup problem. And so here's their kind of syntax. You notice the syntax changes on every slide. And so what they do is that they carry out the foundational verification program, which we know from something like the verified software stack by Andrew Appel and company, or from Rust Belt for Rust by Ralph Young and company. And so it means that you set up your syntax as a deep embedding into Coq as an inductive data type. Then you set up a semantics written from first principles. And then in your program logic, all the rules are lemmas in the semantics. And at that point, you can really do stuff from the ground up, and you can verify stuff like this. So that's the session. And I just want to say that more and more conferences like POPL in computer science are accepting papers in quantum. And I think this decade will see a lot of progress on the software stack for quantum computing. And we just saw 3 languages. Which one is going to be the winner? And I think the winner of languages in quantum computing is going to be invented in the future. So let me sort of say it that way. And otherwise, I would say attend the session and go learn some quantum computing. You can do it.